Okay, so we've been talking about functions and composition and that sort of thing, and we have more to say about that. As soon as I can get this. Yeah. So today's May 1st, wow. So here's the idea. So I'm going to make 3 columns here. So in the add column, we've got the additive identity. That's 0 because x plus 0 is x for all x. So in some sense, what you can understand that to mean, that means that adding 0 is the same as doing nothing. All right. In the multiplication column, multiplication also has an identity. What's the multiplicative identity? 1. Because given any number, multiplying by 1, x multiplied by 1 is just x. So multiplying by 1 is the same as doing nothing. So notice that you can't like mix these around, because adding 0 does nothing, but multiplying by 0 does something, right? So you know, it would be just fine if we took our bank account and we added 0 to the dollars, right? Okay, nothing changed. But if you multiply by 0 and you've got a positive amount of money, that you'd be really upset. Good. Similarly, multiplying by 1 does nothing, but adding 1 does do something. Okay, so that's add and multiply. Those are things that you already knew before you got here to college algebra. The one that we're interested in is composition. And these are statements about numbers, but composition is concerning functions. So specifically, we have something called the composition identity. It is the function whose name is ID. So its name is ID. And it is the function, what's the formula for the ID function? ID of x is what? Is x. So it's the function where you put an x in and, as input, and then x is the output. So you put a 7 in, 7 is the input, 7 is the output. -4 is input, -4 is output. It doesn't do anything. So in this case, what it's saying is that if you compose f composed with ID, well, that's just f. So if you have a function and you compose it with the identity, then the resulting function is the same. Didn't change it. And ID composed with f is f. So we have to write it in both orders for composition because composition doesn't commute. Add commutes, meaning that, for example, 3 plus 5 is 5 plus 3. So x plus 0 is the same as 0 plus x, so we don't have to write it in both orders. Similarly, multiply commutes, but compose doesn't commute because functions represent processes, and generally speaking, processes do not commute. For example, there's the process of putting on your left sock, and there's also the process of putting on your left shoe. Those are 2 different processes, and it does matter what order you do that in, right? One of them is, the way that more or less we get ready for the day, and the other one is, why are you wearing your sock on the outside of your shoe? Okay. 2 is that x and y are called additive inverses when when x plus y is 0. Okay, and then the analogous statement in the case of multiplication is that x and y are called multiplicative inverses when x multiply y is 1. So to really overstress what's being said here, to overemphasize some of the words, is that in focus? It doesn't look like it's in focus to me. Okay, that looks a little better. So to overemphasize what's being said here, we could say it like this. X and y are called additive inverses when you add them and the result is the additive identity. And x and y are said to be multiplicative inverses when you multiply them and the result is the multiplicative identity. So you hear me emphasizing the name of the operation. So similarly, when we're talking about composition, we're composing two functions. So functions f and g are called composition inverses when what? Well, just like when we were asking if they're additive inverses, we added them. And we were asking if they're multiplicative inverses, we multiply them. So now we're asking, are they compositional inverses? Well, evidently we're going to have to compose them probably, right? So we'll compose them. And over here, when we were asking, are they additive inverses, we were looking for the additive identity. And when we were looking for multiplicative inverses, we were looking for the multiplicative identity. And because now that we're looking for compositional inverses, we want the compositional identity. ID. All right. But again, because composition doesn't commute, you have to check it in both orders. So we have a and G composed with F is the identity. Because it's necessary to check both. All right. 3. 3. The formula for additive inverse is, well, its name is negation. So specifically, I could give you an example. I could say, well, what's the additive inverse of 5? Negative 5. Just whatever I said, you just say negative the thing that I just said. So the additive inverse of 5 is negative 5. The additive inverse of negative 8 is negative 8. And of course, under normal circumstances, you would just say 8. So you negate. Fine. The formula for multiplicative inverse is reciprocal. So like, negation 5 to negative 5, or if you like, negative 8 to negative 8. For reciprocal, something like, 5 to 1/5, or negative 2 over 7 to 7 over negative 2. That's the formula. In the end, the reason why this formula works is because, for example, in the case of 5 to negative 5, if you take 5 and you add negative 5, what do you get? 0, which is the definition of what it means for them to be inverses. Similarly, if you take negative 2 over 7 and you multiply it by 7 over negative 2, then notice that the 7's will cancel, the negative 2's will cancel, and what you're left with is 1, which is what it means to be multiplicative inverses. All right. So here's where we are today, is that this is what we want. We want a formula for compositional inverse. So we've got to figure it out. All right. So concerning that, here's the main idea. So finding composition inverse is that it has to do with solving equations. I'm going to start a new page. So, for example, so here's an equation. Y is equal to 3x. So currently, y is solved for and x is not solved for. So suppose I say, well, here's an equation, I want you to solve for x. All right. So x is not solved for because with x is this multiplied by 3. So to get x by itself, in some sense, we've got to get that multiplied by 3 to change sides. It's got to move to the other side. And moving it to the other side causes it to do, basically, you want to know what undoes multiply by 3. Well, divide by 3. So doing that, we get y over 3. So over here, it's multiply by 3. Over here, divide by 3. All right? Not, that's not a deep realization, I think. What about something like y is equal to x minus 4? Again, if we wanted to solve for x, currently x is not solved for. So, we'd want x to be by itself, and this subtract 4 would need to change sides. And to change sides, it has to do, it's sort of like asking, what's the undo button for subtract 4? Well, add 4. Again, this is not deep, not deep insight here, but rather I am setting us up to see that we're trying to figure out how to get everything to undo itself, to become its opposite. Multiply by 3 to divide by 3, subtract 4 to add 4. So how about this one? Y is, say, x to exponent 5. And we want to get x by itself. So it's not by itself because it has that exponent 5. And just to really drive the point home, I'm going to rewrite this equation to remind you that exponent 5, we have a punctuation, a little symbol for that. That's a caret, right? So what we're saying is that this equation is the same as x caret 5, like that. And if we want to get x by itself, we need the caret 5 to change sides. And so the question is that when the caret 5 changes sides, what does it become on the left side? Right. So, but except it's not called square root. Yeah. So it will look like this one. So at first, when you're writing it, it looks just like square root. But then, to indicate that this was a 5 over here, you put the 5 right here. So caret 5 becomes one way to say it is radical 5. Caret 5 to radical 5, or root 5. Okay. Interesting. What if I take an equation very similar to that one, and I write, how about this? Y is x with exponent 6. So the only difference being is that I wrote a 6 instead of 5. So again, this would be y is x caret 6, like that. And now we want the caret 6 to change sides. So at first, if you're not ready for the punchline, you could think, oh, well, it's going to be just like the other one. So the x is here, and the y is here, and we've got a radical, and this is a 6. So the caret 6 just did that. But that's actually not correct, because the caret 6, in fact, is not able to, in some sense, make it all the way over there. It actually ends up leaving something behind. What gets left behind? Absolute value. So it can't make it. Can't make it. Then you might say, oh, you're saying we forgot absolute value here? Then didn't we forget it here? And the answer is no. This one doesn't need absolute value. What's the distinction? Yeah, it's the parity distinction. In the case of an odd exponent, it goes through without leaving any absolute value behind. But in the case of an even exponent, you can't make it. So if you look at the last example that we did last time, I gave us two functions, and I said, determine if they are composition inverses. And it turned out that in one order, if you compose them, in one order, you get x, which means that their inverse is in one order, but not in the other order. And in the end, it was because we were using an even exponent. It was a square. So one of the times, it didn't simplify down to x. It simplified down to absolute value of x. Right? Good. So in order to find a composition inverse, so to find a composition inverse, in the end, the process looks like this, is that you say, well, we've got some function, f, like that, and then we want to solve for x. So just like for this, we said, well, we want the 3 to go to the other side. So multiply by 3, the opposite of that is divide by 3. Oh, we want the subtract 4 to go to the other side. So subtract 4 to add 4. So what we're saying is that f just represents whatever's happening. That's just a name for whatever is happening, and we want the f to go to the other side so that x will be by itself. So x is over there, y is over there, and the way that you write opposite of f, just like multiply by 3, divide by 3, subtract 4, add 4. The way that you write opposite of f is as an f, but with a superscript -1. Like that. So that's how it gets written. So that is pronounced. So f superscript -1 is pronounced. Composition inverse of f. All right. And then when you are in a hurry or just being sloppy, you could pronounce it as f inverse. But in my view, it's a little bit sloppy to say f inverse because, you know, on this page right here, on this page right here, we have 3 different kinds of inverse. So if you say F inverse, are you saying additive inverse, multiplicative inverse, compositional inverse, some other kind of inverse? All right. Then we'll do one last step, where we say, okay, we're going to swap. X's and Y's, which is to say that we're going to rewrite exactly this thing. But we're going to replace all the Y's with X's and all the X's with Y's. So rewrite exactly that formula, but like this. Okay, so here's an example. So find, let q of x be 4x cubed plus 1. Find q inverse, composition inverse. Find q inverse, and then you may assume it exists. So now the reason why I'm adding this last sentence, you may assume that it exists, is because after we go about figuring out how to find it, the next thing we're going to talk about is when do they exist. So later the question will not read like this. It'll say let q be this function, and then it'll say the first question will be determine if the inverse exists, and explain why it does or doesn't exist. And then if it exists, find it. So me saying you may assume that it exists, I'm basically saying that when you're looking back at this, that just means that whole part of the question is cut from this one. Okay, so here we go. So you start out by writing this function here. And now the first thing is just to replace q of x with y. All right. So now we're going to solve for x. So x is not currently solved for, but that's what we want to achieve. All right. So I can see that, you can think about it either in a number of ways. So on the one hand, we could say I'll transfer the plus 1 to the other side. So what does it become when you move it to the other side? Yeah, subtract 1. Or you could say it like this. I'll subtract 1 from both sides. All right. So now it looks like y minus 1 is 4x cubed. All right, now what? And you can think about it 2 ways. You could either say, I'll divide both sides by 4, or you can say, well, I have this multiply by 4 on the right, and I want to transfer it to the left. So when it transfers to the left, it's divide by 4. However you want to think about it. Okay. Now what? Yeah, you can either say, well, I've got caret 3, exponent 3 over here, and I want to transfer it to the other side. So transferring it to the other side, it becomes radical 3. Or, if you like, you could say, I'll compute the cube root of both sides. Okay, but this is caret 3. Is it able to completely transfer to the other side, or does it leave behind junk? Yeah, it makes it all the way. Why? How can you tell? It's odd. All right. Y minus 1 over 4 cubed like that, and then this is x. All right. So all of this, this was solve for x. You know, we did it in 3 or 4 steps there. In general, it could take, you know, less steps or more steps, but you gotta get it figured out. So now we're going to do that last thing, and that is that now that we have x solved for, we're going to swap x's and y's. Which is to say, we're going to write down exactly that formula, except everywhere that we see y, we'll write x, and everywhere we see x, we'll write y, so that it looks like x minus 1 over 4 cube root is y. And now we can say, therefore, q inverse of x is exactly that stuff that is opposite to y there. It's this, cube root of x minus 1 over 4. So now, to sort of explain what it was that we did here, on the one hand, you could just say, well, you know, we just did that thing, that thing, that thing. But on the other hand, I could say, well, you know, if I came to you and said, here's a 4, the number 4, how do you find its additive inverse? It takes a little bit of work, not much. So what is the additive inverse of 4? Negative 4, right? So that was like, you know, that much work, you know, just a little bit. And alternatively, I could walk up to you and say, hey, here's a 7. Could you please find the multiplicative inverse of 7? Well, 1 over 7. Well, you know, that required, you know, a little bit of work. So what I'm saying is that what I did is I walked up to you and said, hey, here's a function. Q of x is 4x cubed plus 1. Could you please find its compositional inverse? Well, it requires a little bit more work, right? It's more than finding an additive inverse or a multiplicative inverse. But in the end, it's a little bit of work. So if this was part A, if that was part A, then part B, I could say, now verify your Q inverse of x really is the composition inverse. So how do you do that? Well, you mean do exactly this, but in the other order? That's a good idea, but it's not enough. Rather, what you must do is you have to compose it with Q in both orders. So you'd have to do the following calculation. You say, well, I'll do Q composed with Q inverse, evaluate at x. And then writing this without the composition symbol, that means Q of Q inverse of x, like that. And then, you know, you can remember that we did it last time. There's usually a whole bunch of algebra, so I'm gonna, for time, I'm gonna skip it. So ... And you know, because you know, assuming that we did all this right, we have an expectation. What should this all simplify down to? X. Okay, so you know the ... that's something that you would have to show. You have to do that part. But this would not be enough. What else must we do? Yeah, I have to do this in the other order, right? So and Q inverse composed with Q, evaluate at x. So, you know, writing that without the composition symbol like this, you know, ... and you should get, this should all simplify down to x in that order also. So you'd have to show this stuff that that I'm omitting. All right, very good. Any question about this? So in the end, finding a composition inverse basically just comes down to, you know, solving an equation. All right. Now, every number has an additive inverse, but only non-zero numbers have multiplicative inverses. And so you could sort of think of that like, you know, almost every number has a multiplicative inverse. But as it turns out, you know, you kind of think that where functions are concerned, they're really mixed. Some of them have composition inverses and some of them don't. So we need to figure out which ones do and which ones don't. So which functions have a composition inverse? All right. So here's the main idea. So remember that when we first started talking about functions, we said there's such a thing as a relation, and we drew it as two boxes with stuff in it, and then we drew arrows. So we're back to that. So if we have such a thing, so how about 1, 2, 3, this will be the domain, and AB, this will be the codomain. Like that. So a relation is where you draw arrows from the domain to the codomain, and you can draw as many arrows that you want as you want. You could say 1 goes to A and to B, and maybe it even goes to B again. You know, you can do all kinds of crazy stuff. But to be a function, you draw one arrow from everything in the domain over to the codomain, and however you want. So maybe 1 goes to B, like that, and 2 to A, and maybe 3 goes to B. And you know, we said that you know, relations are when you draw the arrows however you want, but functions, to be a function, you can only have one arrow leaving. So notice that one arrow leaves 1, one arrow leaves 2, one arrow leaves 3. So one arrow leaves every element. Of the domain. And to sort of emphasize what I mean by that, what I mean by 1 is I mean exactly 1. So there can't be 2, there can't be 0. Okay, good. Fine. So now if this is some big machine and you're over here at the output side, like that, and then your buddy is over here on the input side, but you can't see them because it's like a big machine. All that you can see is the outputs, and you know exactly the way the machine works. Then, all right, what if you witness an A come out? Do you know for sure what if you think of these like buttons, do you know for sure what button was pressed? If you witness an A come out? Yeah, they must have pushed button number 2, because that's the only way to get an A. But if you witness a B come out, do you know for sure what button they pressed? No, they could have pressed button number 1 or 3, and you can't tell. Can't tell. So now, here's a function, and what we're going to do is we're going to make a modification to this machine, is I'm going to make a copy of it. So I'm going to copy exactly the same machine, except now I'm going to say that this is the domain, And this thing over here is the codomain. And I'm going to keep the connections the same, so 1 is still connected to B, but I'm going to turn the arrow around so that it's still 1 is connected to B, but now it's pointing that way. And it's still 2 is connected to A, but is pointed that way. And 3 is connected to B, but pointed that way. All right. So anytime you draw something like this, it is a relation. So this is a relation for sure. But the question is it a function? Okay. No. Why is it not a function? Yeah, because B is going to 2 things. B is going to 1 and also to 3. So to be a function, to make a vending machine analogy, if we walk out to that vending machine out there, and if we imagine for a moment that money is not required, only button presses, then that vending machine is a function because when you push one button, one item is vended, right? If there was a button that you pressed and 2 things were vended, well, 2 things, the little rolly springs roll and then 2 things come out, then the vending machine is not a function. So this would be like a vending machine where you press button A and you get item 2, but you press button B and items 1 and 3 come out. Well, that's not a function. Okay, so this is not a function. So what I'm saying is that when we did this, from here to here, the modification that we made is we turned the arrows around. Or if you like, you could say we inverted the arrows. And so this is a function, but it's not going to have a composition inverse. So not a function, so we can say therefore there is no composition inverse. So here's an example of a function that doesn't have a composition inverse. It doesn't have a composition inverse because when you turn it around, the result isn't still a function. All right. So here's an example. When the composition inverse does exist. So in the end, the problem here is that we had 3 to 2. In order for it to be a function going both ways, we're going to need the same number of elements on both sides. So I'll do 3 and 3. So if it looks like this, say 1, 2, 3, ABC, one to C, 2 to A, 3 to B, then and suppose that I name this this thing F, just to give it a name. Then what we're saying, is that you plug in 1, you get a C. You plug in 2, you get an A. You plug in 3, you get a B. Do you observe that that it's a function because 1 arrow leaves? And if we turn the arrows around, do you see that the result is still a function? So what I'm going to do is right next to it, I'm going to do I'm going to draw the inverse. So this is going to be F inverse. But instead of turning the arrows around, rather what I'm going to do is I'm going to physically move the domain and the codomain. So this box is going to be ABC. And this box over here is going to be 1, 2, 3. You know, 1 to C, but I still need the arrows going to the right. Similarly, 2 to A, so like this, and 3 to B. All right. So now, the reason why these are inverse functions, the reason why you can see it, is that you can imagine, oh, we built this one, and now suppose we put this in one big box, one big container, and say, okay, I'm going to you know, make a big thing like this. So now they're all inside of a big box. And to indicate that I'm composing what I'm doing, I'm going to say this A is connected to that A, this B to that B, and this C to that C. Well, the name of this thing this you know, loud monstrosity that we've built here, its name is F inverse composed with F. So let's look and see what happens. What if you put a 1 in the machine? Then 1 goes to C, to 1. So if you put a 1 in, what comes out? A 1. What if you put in a 2? 2 goes to A, which goes to 2. So if you put a 2 in, a 2 comes out. What if you put a 3 in? 3 goes to B, which goes to 3. So what this is a complicated way to say nothing. You put a 1 in, 1 comes out. You put a 2 in, 2 comes out. You put a 3 in, 3 comes out. And if I cut this machine in half and then put these in the other order and redid these wirings in the middle, then it would be A to A, B to B, C to C. Ah, very good. Any question about this? So the main idea is that to be a function, all such things are relations, but to be a function, there has to be one arrow leaving. And then, given a function, for it to have an inverse, there has to be one arrow arriving, not 2. Now, visually, the way that manifests itself in our class is with the following. So these are called the line tests. So, you know, when you're looking at diagrams like these, the test, if it is a function, is there one arrow leaving? But when we're drawing functions, typically we want to draw them on x, y axes. So, a graph is the graph of a function if every vertical line intersects the plot at most once. Okay, so here's 3 plots on an xy axis.